Hi guys, and welcome back to Electronics with Ben, and today we're going to be looking at a capacitor construction task. Now the task itself is on the screen already, and we've been given some values here. That's the specification we've been provided with. We've also been given a circuit diagram and a DC voltage of 40 volts, and we've got to do four things below. So we're finding a single value of capacitance, total value of circuit capacitance, voltage across each one of the capacitors, and the total charge stored and the energy available for the above combination. Now in order to do this, we are going to have to use our C equals EOERA over D formula. And the way the formula works, I'm going to highlight some of these points for you, is that we extract the values from the given specification, put them into the formula, put them in our calculators, and then we have got a single value of capacitance. Now in terms of what goes where, EO, this is the electric constant, and this is always 8.854 times 10 to the minus 12. So even if you're doing different variations of this formula, you will always use that EO value, and it will always be the same, 8.854 times 10 to the minus 12. Next we need to put in ER. Now ER, as it's stated, is the relative dielectric constant of the material, or the permittivity. As you can see, the permittivity here is 7.8, and ER value goes there, so this is where our 7.8 value will go. Next in the formula is the area. So in the specification it is the plate area, or the cross-sectional area, or effective CSA, and this has been given to us as 60 millimeters squared, and this goes in there. Now what you will note is that I've put it in as 60 times 10 to the minus 6, and the reason for that is we need to convert it from millimeters into meters. And with it being a squared value, we have to divide it by 1,000 and then divide it by 1,000 again. Hence why it's times 10 to the minus 6. It's effectively dividing it by 1,000,000. The last value that we're going to have a quick look at is the distance between the plates, and this distance has been given to us as a sheet thickness, which is exactly the same. It's effectively saying that it's the distance between the plates, or the thickness, and this is the D at the bottom, and you can see again we've divided this by 1,000 to convert it from millimeters into meters. Now if you put all those values into your calculator and press the equals button, hopefully you should be presented or produced given a value of 4.14 times 10 to the minus 12. And recalling what we know about our engineering notation and prefixes, etc., that times 10 to the minus 12 is the same as pico. We're dealing with capacitance. The unit of capacitance is farads, so for a single value of capacitor it should be 4.14 picofarads. So that is the value of a single capacitance in picofarads. So we have done the first bit of the question right there. The next part is the value of the total circuit capacitance, and for this we need to go back up to our circuit diagram here and analyse what's going off with that. Now in terms of the way it's laid out, we can see that the first capacitor, call it C1 if you will, that'll be connected in series. Then we've got two other capacitors, and we could perhaps call these C2 and C3. They are connected in parallel. Now the good thing is parallel capacitance is easy, and that's the bit that we'll be working out first. So when it comes to determine parallel capacitance, we can simply add them together. So if we note down that the parallel part of the circuit, you'll have to excuse my joined up handwriting, is two 4.14 picofarad capacitors, and for the process of people that are just checking this in the calculators, we'll write them as times 10 to the minus 12. we're just going to simply add them together. So it's going to be 4.14 times 10 to the minus 12, add 4.14 times 10 to the minus 12, and when we add them together, you should get roughly 8.29. My rounding may be a little bit random, but you get the idea. And that again will be in picofarads. So that is the parallel part taken care of. Now what we need to do is establish the series part, and now effectively what we've changed is we've now created a circuit with two equivalent series capacitances. So we can redraw that as this is the first capacitor, that stays the same. We've now got a second capacitor with a new value of 8.29 picofarads. The first capacitor value will remain the same, and that will be 4.14 because it's the same as what we used when we calculated it initially. So now for that new circuit, we can effectively draw up a new formula to calculate the total. So we want the total capacitance of that circuit there. Now in order to do that, we do our trusted 1 over formula, because series capacitance needs to be calculated using what we've called the 1 over method. So in our calculators, we will do 1 over 4.14 times 10 to the minus 12 plus 1 over 8.29 times 10 to the minus 12. And you should be able to do that all in one go, and hopefully we will get a value of 2.76 times 10 to the minus 12, or picofarads. Now this value is our total circuit capacitance. So we've got a single value of capacitance, which is our 4.14 picofarads, and we've got a total circuit capacitance of 2.76 picofarads. It's not unusual for the total to be less than a single value, and that's due to the fact that it's got series elements which, when you do the 1 over method, will always give you a smaller value. Now the next question prompts us to work out the voltage across each capacitor. Now to do that, we need to break it down into some further steps. And the first step being is we need to first of all work out the charge value for the circuit. Now charge, as we spoke about before, is the formula of Q equals C times V. And your Q will be your charge, C will be your capacitance, and V, as you can assume, is voltage. Now we need to work out total charge first. So what we're going to do is take our total capacitance value and multiply it by our total voltage. Now we've just worked out our total capacitance value. That's there as 2.76 times 10 to the minus 12. So that we can dial straight in there. 2.76 picofarads, which times 10 to the minus 12. We then need to multiply that by our total voltage. Now total voltage was given to us in the question there. That's our total voltage, so we times it by 40. When you put that in your calculator, you should come out with 110, roughly about 0.43. Again, rounding might be different, and that's still pico, so times 10 to the minus 12, and charge is measured in coulombs. So we can put this as picocoulombs, little p, big C. So that is our total charge, our Q value for this circuit. Now we've got total charge, we can work out, by transposing this formula, the voltage dropped across the first capacitor. Now when we transpose our charge formula, it's Probably easier to represent it in this triangular format here. And by this one, we can effectively cover up what we are trying to calculate, and then it prompts us how to transpose the formula. Now we're wanting to calculate voltage, I believe. So yeah, the voltage across each capacitor. So we'll start off with capacitor number 1. Now the capacitor number 1 is this value there, 4.14 picofarads. Now when we transpose our formula, if we cover up voltage, it prompts us to do charge divided by capacitor value, and we're going to do capacitor number 1. Now the best way to kind of remember this and write it down is if we want voltage in capacitor number 1, we have to use the value of capacitor number 1. So when we transposed our formula, it will be Q, which is total charge, we've only got one value for that, and it will be C1, because that's our capacitor number 1 that we want to find the voltage across, and that will effectively give us V1. So now when we dial those numbers in to our formula, we're going to take the 110.43 that we've just worked out. And remember, it's times 10 to the minus 12. We're going to divide that by our first capacitor value in the circuit, which is there, which is 4.14. And again, it's picofarads, so it's times 10 to the minus 12. Then when you do that, you will get, or you should get, 26.67 roughly. Again, rounding might be slightly different. Now, this is the voltage across C1. So if we go back to our diagram at the start of the question, this is the voltage dropped across here. So if we had a voltmeter, put it across there, it would tell us we've used up roughly 26.5 volts. Now the good thing about that is we can now cast our minds back to resistors and series resistor theory and a little bit of Kirchhoff's voltage law. Now if we start with 40 volts, and that's across the whole circuit, so between kind of there and there, we're going to use up 26.5. What's left is going to be distributed across those two capacitors. So in terms of the voltage across each capacitor, which is what we need to do now, we just take our total supply and minus the voltage dropped across C1. So in order to do that, it's effectively VT, which is the voltage total, minus kind of the voltage across C1, so VC1. And when we kind of write that down across here, we can just say, when we plug our values in, 40 volts minus 26.67 volts, or what you rounded it to, you can say roughly will give us a remainder of 13.32 volts, roughly. I know that doesn't add up exactly, but it's close enough. Now, good thing about that is, and what we already know about voltage in parallel, it will be distributed to that capacitor and also that capacitor. So if we call that C2 and we call that C3, we can now say we've calculated the voltage across all the capacitors. We did the charge transposition for C1 voltage, and we've now minused that voltage away from the supply, and we've got a voltage for C1 and C2. So effectively, that is C1V C2V is equal to that 13 value there. So that is that part of the question solved, which leaves us really with one final step, and that is the total charge stored and the energy available for the combination. Now for this, the total charge stored we've already done. That's there, so we don't need to do that again. Depending on how the question's set out, you can just rewrite it. If you want to show off and be all fancy, you can rewrite the whole formula with the correct transposition, or just direct it to the section above. What we do need to do, however, is finish off the energy stored. Now the energy stored calculation is the one where it's W is equal to a half, or 0.5, and then that's times by capacitance, and that'll be the capacitance total times voltage total squared. Now we've got all these values from before, so when we come to fill out this formula, I always do it as 0.5 because it's quicker than faffing with the fraction button on your calculator, times total capacitance, which we worked out as 2.76 picofarads. So the main bit to remember here is that it's 2.76 times 10 to the minus 12, and then we times that by our total voltage squared. And our total voltage was provided to us in the question as part of the specification. So we would write that as 40 squared. When we put that in our calculator, that will give us an answer in joules, and I believe that W is equal to 2.208, and that'll be times 10 to the minus 9, and that is 2.208. N is nano and the unit is joules, so it's nanojoules, like that. And I believe that concludes the question, and we've answered all the parts of it. So as you can see, there's a fair bit of working out involved in order to solve the whole question. However, if you follow this guide, methodically work your way through, referring back to previous calculations, you should be able to successfully solve any question with similar values to that. If you like this video, please feel free to comment, like and subscribe, and stay tuned for more further content from Electronics with Ben. Bye guys.